start with this Cox proportional hazard analysis, and we'll see how it is very much similar to the logistic regression. So those of you who have done logistic regression, the analysis and analysis that is there, but the interpretation of hazard ratio is very much similar to the odds ratio. And we'll see that. How? So this was the article which we have shared with you people, like breastfeeding education, early skin-to-skin contact, and other strong determinants of exclusive breastfeeding in an urban population, a prospective study. So in taking the same example, so suppose we want to see the effect of mother marital status. Marital status, we have classified it as single, where the mother was not married with the others, on the termination of exclusive breastfeeding. And we have shared the data set also with you people. So I have asked you that that you should perform the analysis, all the three analysis, and then see how they have done it and how your output is coming. So, and this is published in BMJ Open, and we'll see like these days how like even the article or the journal, they are accepting that kind of tables and the kind of output they expect. So here we used Kaplan-Meier method of estimation of survival curve for other and single category, and the author has classified it like this. So this was, you have just done it, that this is the unadjusted survival curve for the marital status of mother for the termination of breastfeeding. So if you see this we will see, and maybe you must have seen this, that this is the levels. So for any explanatory variable, if you take the dependent and independent variable, so in logistic regression, what do? We have got a dependent variable which has got a two levels, and then you have got a independent variable which can be a continuous variable, ordinal variable, or a nominal variable. Here, if you see these levels, so this is other and this is single. Single means like the mothers are not married. So if you see the hazard ratio, this is the HR, which is the hazard ratio, which is the univariable. Univariable means it is the unadjusted, because we are taking only one explanatory variable. That's why it is known as the univariable. This is 1.45 with a confidence interval of 1.07 to 1.97 with a significant p-value. This you can see. So this is your unadjusted hazard ratio, and this is your unadjusted survival curve. So here the Kaplan-Meier curve provides a clear visual representation of survival probability over time. If you see this, Kaplan-Meier is also giving you the survival probability, and you can see that this is a green one. Green is the other. So the survival probability is better with the other marital status, and this orange one is for the single. So it has got a poor survival rate, because in Kaplan-Meier we know that curve which is above, that has got better survival probability. So this was from the Kaplan-Meier. This is Cox proportional. So I'm not discussing now Cox. So I'm just telling you what advantage does this Cox proportional hazard model gives you over the Kaplan-Meier estimation. This is again the other variable which I have taken, that was the education. So education has been classified as higher education and lower education. And if you see this Kaplan-Meier, you will see that this orange one, which was the lower education, it has got a better probability. And so it gives you a clear visual representation of survival probability over time for each level of education, showing that the mother with higher level of education had poor survival rate. So we can think like, so is there any possibility that mothers who are having higher educational status are also a single marital status? Maybe there may be more unmarried women in that higher educational status. So the effect of this educational status which we are getting we getting due to the educational status or due to the single status? So yes, what is your answer? So in this case, can you think that maybe this single marital status are more in the higher educational status? What is your answer? Yes or no? Yes. So Dr. Girish is writing yes. Okay. Then again, this is okay. Priya is writing no. So here we are discussing that if you are studying one variable, then what is the problem? That you can know the effect of that variable only. But in natural phenomena or in whatever disease or the natural history of disease, there are many variables which are acting on the outcome variable. But there is this limitation is there with Kaplan-Meier survival, that it does not account for other variable. Like you can only study single variable, maybe only single gender or maybe educational status or skin to skin contact, etc. But in general, you have got many more variable. That's why there is a utility of this Cox proportional hazard model, and this is a very useful model. It has got a very high utility because it gives you the adjusted hazard, because through this univariate you will get univariable, you will get the unadjusted hazard, like we get in the odds ratio. You have got a unadjusted odds ratio, you have got a adjusted odds ratio. So this Cox proportional hazard model is of very high utility because it allows us to include these additional variable also in the analysis. And by doing so, then we can understand like whether it is due to the marital status or the other factor like education. It is also, there's an interplay between these variables. So you can see that this is the adjusted survival curve for marital status of mother for termination of breastfeeding. And here it is adjusted for gender of the baby, educational status of the mother, skin to skin contact, breastfeeding within 1 hour, and the education session taken. So this is the adjusted. We'll show how to do that. And you can see that here, that again, the single, they have got a poor survival, and the other category, they have got a better survival. So adjustment in the survival curve, which you have seen, that is in context of using the Cox proportional hazard model, because there only you can control for the other variable while taking the effect of marital status on the duration of exclusive breastfeeding. So after adjustment, you might find that the initial observation, what mother with single marital status, they have breastfed exclusively for a shorter period, that is still valid, even after controlling for the other factors like education of the mother, baby, gender, any other factor. So then you can say that the marital status is an independent predictor of the exclusive breastfeeding duration. And again, the relationship between the marital status and breastfeeding duration, this changes after, whether it gets changed after adjustment or not. And it could indicate that whatever duration you are observing, that is the observed survival, is it there at the different levels of the other factor like the mother education, skin to skin contact, and any other variable. So if there is a change in relationship after you, we'll see that if there is a change in relationship between the predictor variable on the dependent variable, then it is known as confounding. So you know confounding, and it occurs when there is a effect of like the primary variable of interest, it is mixed with the effect of other variable that are also associated with the outcome. So this Cox proportional hazard model, this adjusts for the confounder, especially the known confounder, because then you take all those confounding factors in the analysis and then it gives you the adjusted effect or the adjusted hazard ratio. So the estimation of this adjusted hazard ratio, this Cox model estimates the hazard ratio for the primary exposure, and it controls the other confounding variable constant. And what do we mean by that? That it calculates the effect of primary exposure on the outcome as if all the study subjects were same with respect to the confounding variable. Now there is one key assumption in this proportional hazard. We'll see how to check that. And that key assumption is that the effect of these covariates are multiplicative and constant over time. What do we mean? We mean that the hazard ratio for the primary exposure is assumed to be proportional and does not change over the study period. And this is known as the proportional hazard assumption. Let's understand this with a simple mathematics. So you can see this, that this is a girl and this is a boy. So if like you are taking any outcome, so this is the start time. So the start time, it is the, you need to maintain, if you need to maintain the same difference between male and female at each time point, this is 0, this is 2. So what value you will write here? And this, if I ask you, what value you will write here? So what will you write? If I want to have a constant difference between these two, so initial difference is 2. So what value should I put here? Yes, let me see the chat box.
3.
So if you put 3, then the difference will be 1.5. But here the difference is 2.
2. Okay. So it is 3.5.
Yes, true. It is 3.5. What about this next one?
5.5.
Agree. And then 5.8 and 6.4. So true. Rightly said. Now, if I need to maintain the same ratio between male and female, initially it was a difference. Now it is the ratio. So you can say that this is female and this is male. So this is, if you take like male taking female as a reference. So maybe if I'm taking female as a reference, so 2 by 1. So it is 2. So now what about this? The next one?
3.
3. Okay, good. And then this one?
7.
Good. And similarly, you can multiply and you can get it. So it is not exactly same. You will see that if this is not exactly same, but it is nearly same. So now you consider a hypothetical study to see the effect of gender on the second attack of MI over a span of time. Like remember on day, but that is yesterday we discussed about the experience of the second attack of MI in both male and female. And if you have to see this, so this is the hazard ratio. Now I have introduced a term hazard ratio. What is this hazard ratio? Hazard ratio is the ratio between the two hazard rate. Remember yesterday we talked about the hazard rate. What is a hazard or hazard rate? Hazard rate is basically the instantaneous potential in small time t of experiencing that event. Event is the failure. So hazard rate in male and hazard rate in female. If you take a ratio of these two, it is the hazard ratio. So you can think of like hazard rate as an odds. Because when you take the ratio, this becomes odds ratio. I'm talking about the logistic regression. Now, in the similar analogy, if you see this hazard ratio, so the ratio between the two, ratio of two hazard rate, it is known as the hazard ratio. And you can see that if this is at a start point, so this ratio is like if I take female as a reference, so what is the ratio? 1.2. So now, all of you please take out this ratio of at 3 months. So how will I take it? 2.6 by 2.2. So all of you please do that. So what is the value? If you like do 1.18. So it is nearly 1.2 or then 3.7 by 3.1. What will be the value?
1.19.
1.19. Agree? 4.2 divided by 3.5?
1.2.
Okay. So you can agree. So you can see that there is a same hazard ratio across all time points. Can you see this?
Yeah.
Okay. So this is known as the proportional hazard. Although you will assumption. So proportional as hazard in both the categories changing. It is not like the hazard is same. Hazard is increasing in female also and in male also. But this ratio is almost nearly constant at each time point. This assumption is known as the proportional hazard assumption. So in this example, can we say that the effect of gender on second heart attack is same across each time point? Can we say that? Because if you see this, so even if whether it is at every time point, the hazard ratio is same in male and female. That means there is effect of gender that we can say that it is same across each time point. Now consider this example. So this is 1.2, but now take out this ratio 2.5 by 2.2. What will be the value?
1.13.
1.18. So now again next one, 3.5 by 3.1.
1.12.
And then 3.9 by 3.5.
1.11.
And 5.2 by 4.6.
1.13.
So it is approximately, it is, if you take that up till one digit, approximately it is same. Right. It is not exactly, but so can we say now that the effect of gender on second heart attack is nearly same across all various time points? Can we say like that? Because the ratio was nearly same here as compared to the previous one. But now consider this new result in comparison with the previous. So can you do this calculation once again for me, like 3.4 by 2.2? What will be the value?
1.54.
1.54. And then this 1.8 by 3.1.
0.58.
Yes, so this is just reversed. So you will see that now the this hazard ratio has started decreasing. So can we say here that the effect of gender on second attack of MI or heart attack is nearly same across all time point? Can we say like that? In this case,
No.
No, we cannot say true, because we can say that the hazard ratio is changing. So gender had a different effect on the second attack of MI across various time points. So do you agree with this statement?
Yes.
Yes or no? Yes. So this is this assumption. So in this here, you can say that the proportional hazard assumption was not met, right? So that's why the name is the Cox proportional hazard. So if you see this survival analysis here, why do we do the survival analysis and this Kaplan-Meier and the this instantaneous calculation of hazard rate? Because rates are not constant even for a shorter period of time. We have seen that if the risk of death, it is in the initial period, it is very high. And as the patient progresses, the risk of death falls. So the rate is not same across all time point. Again, if you see the recurrence rate of tumor, it is again very changing. Like that means initially the recurrence rate of tumor, it is high, and later it might decrease. So this hazard, which is explained as H as a function of T, HT, it is an instantaneous rate at time T, which keeps on changing. That's why we call it as instantaneous. That means in a very less delta T, that is the mathematical explanation, like a form, like we write. So that small delta T, in that small time, whatever is the instantaneous potential of that event to happen, that is the hazard rate or hazard. So now this Cox proportional hazard, you can see there is a term proportional. That word is there. So here, why? Because we assume that this proportion of this ratio of hazard will be same across all time points. So here we assume that the hazard rate, this H1 and H0, that is between the two group, like maybe this can be intervention group and this is the reference group. It is a constant. So H1T is the hazard rate in the exposed group at time T, and H0T is the hazard rate in the unexposed group in time T. So this assumption is known as the proportional hazard assumption. So now, so this is we call it as a Nelson-Allen estimate of the cumulative hazard function. And this is expressed as H1t by H0t. It is always a constant. So now we can see, we know that why do we use this Cox proportional hazard model? Because there in Kaplan-Meier survival, you can have only one variable. You can't have many variables to adjust. But in this case, Cox regression, you can use the multiple predictor variable, and they can be continuous or binary like we do in the logistic regression. So this is also known as the Cox proportional regression method. Both are same. Cox proportional hazard model and Cox proportional regression method are same. And analysis is very much similar. Even the interpretation is very much similar to the logistic regression. The result of logistic regression is expressed as odds ratio, whereas result of the Cox proportional regression method is expressed as hazard ratio. Now, although in Kaplan-Meier survival, here also there are assumptions which we should check. So first assumption is the proportional hazard assumption. So there is one problem in GEMOV that you cannot check this assumption because it is usually checked by the log minus log curve. Like in that interface, that option is not there. So you can check it on the SPSS. And the second is the multicollinearity. So what is multicollinearity? So multicollinearity, when there are more than one continuous variable as a predictor variable, then there should not be a high correlation between those two. Why? Because then you will not come to know that the effect is because of the one variable or the other variable. So that should be checked. It can be checked using a standard error value, which is there in the table in the SPSS, but not in GEMOV. Or it can be also checked performing a correlation matrix. And the value of correlation coefficient should not be, it should be less than 0.8, or you can have like 0.7, 0.8, less than that. It should not be very high. Otherwise, you have to drop one variable. So now this proportional hazard assumption, we know how to check for that. So this, I'm just skipping because in this we cannot check. So now hazard ratio, we know that it is the time to event analysis. And here hazard rate, how do we express hazard rate? That it is in the numerator, we take the hazard in the treatment arm. In denominator, we take in the hazard in the control arm. So what is the hazard? And if you are calculating it across gender, then maybe you have to take the reference category. So if it is a categorical variable, so the reference category is always there in the denominator. So hazard maybe in the male as compared to the female, if you are taking female as a reference category. So it is just like logistic regression. So hazard is an instantaneous event rate, which is a probability that an individual at time t has an event at that time. So now how to interpret this hazard ratio? So again, this is like odds ratio. So hazard rate, this takes into account of both the number of events and timing of each event. Because if you see the odds ratio, what happens there? It is only the odds ratio of the odds. But in case of a hazard ratio, you take time also because it is the time to event data. So if the value of this hazard ratio is 0.5, what will you say? So you will say that at any particular time, half as many patients in the treatment group are experiencing an event as compared to the control group. Similarly, if the value of hazard ratio is 1, then you can say that the event rates are same in both groups. And if the value of hazard rate is 2, then you can say that any particular time, twice as many patients in the treatment group are experiencing an event as compared to the control group. So like this is the mathematical expression. In linear regression, we express the equation like this, where y is the dependent variable is equal to beta 0, which is a constant, plus these are the coefficients, beta 1, x1, beta 2, x2, and this x1, x2 are the predictor variable. Here in case of a hazard, it is expressed like hazard is h at time t is equal to h0, which is like H0 at time t, into this exponent, and then in the bracket we take beta 1 x1 plus beta 2 x2 like this. So if you have to remove this exponent, then there is a way that you have to take a log. So you divide both the side by h0t and take a log of it. So this log by this, you can remove this exponent. So this ht by h0, it is the hazard ratio. So it is interpreted in the same way as that of odds ratio. And it can be interpreted as like 100, and in the bracket, it is the hazard ratio minus 1. That is the percentage change in the hazard when the covariate increases by 1 unit. And this sign, it will convey the direction of increase or decrease. We'll see that with one example. So I will again explain, because this interpretation of hazard ratio is very important. So it is interpreted the same way as that of odds ratio, and we have just seen how to interpret if there is a hazard ratio of 0.1, 1 or 2. And if it is like sign, because you always deduct 1 from the hazard ratio and then multiply it by the 100. And that much percentage change in the hazard occurs when the covariate increases by 1 unit. This is when the independent variable is a continuous variable. When the independent variable is a categorical, then you explain it with context of the reference category. Right. Like in this example, you can see, what can you see here, that there is a curve. This is a hazard curve, and you can see that this is a cumulative incidence of the hazard, and on the x-axis it is the time. So you can see the hazard ratio here, it is 0.64. So this dash line is the treatment with the atorvastatin, and this solid line is the placebo. So you can see that hazard, it is 0.64. So how will I interpret? Remember, I said that you deduct 1 from this. So 0.64 minus 1 will be how much? It will be minus 0.36 and multiply it by 100. So 36%. So sign will show whether it is increase or decrease. So what will you write? That there will be 36% less hazard in the atorvastatin group as compared to the placebo. So this, because placebo is up, so placebo has got higher. It is opposite of survival. In case of hazard, if the curve is upper, that means it is experiencing the high rate of hazard. So this solid is the atorvastatin. So you can say that atorvastatin group has 36% less hazard of experiencing the event at a given point of time. And this is the number at risk, which is, you can see, this is the risk set, which we explained. So this is a very common, like a odds ratio. So now there is a problem of multicollinearity. If there are more than one, if the independent variable, there are more than one continuous variable, then you have to check with the correlation matrix. There is a like value of this standard error also, but Jamovi as a part of table doesn't yield this standard error. That's why we will check with the correlation matrix. So we'll see how to run the commands. So let's see the questions first. So the question is, like here I have to perform a univariable proportional hazard and multivariable. So I'll show this multivariable because using this option, you can perform the univariable also. So here I have to do the proportional hazard assumption, and the other variable, all the other variable which are there, I have to take that. So I'll go on this Jamovi. So in Jamovi, if you see, this was the survival. So we have used this univariate survival analysis till now for the life table. We have seen this option and we have seen this survival analysis. Now we will see the third option because there are many modules. That's why I was just revising that these two we have seen. Now we will use this multivariable survival analysis. Can you see this? So if you click this, then this window will appear. So in this window, what can you see? There are few options. This is the time elapsed, which we have seen earlier. This is the outcome, which this we have also seen. And here there are two boxes. So the explanatory variable, which are ordinal. Can you see this sign? So this is ordinal and this is nominal. So nominal and ordinal variable you will enter in this box. And this is the scale variable. So scale variable you will enter in this box. So is this interface is clear to you people? Can you see? So this is the same. This we have seen earlier, but here in the multivariable you will see that there are two different boxes. So this I will enter this time elapsed here. Outcome, you know, this is the event. This censored, I have to show that this is the termination of breastfeeding, exclusive breastfeeding. Now, what variable you should take as an explanatory and continuous, like categorical or continuous? So what do we do in the logistic regression? How do we decide for the cutoff? What variable to take? Yes, I want to know from you people, those of you who have done. Anyone? How do you decide which variable to take as an explanatory variable based on which criteria?
Binary outcome.
Agree? So you see the unadjusted. And then you see like value of p-value. Yes, Ria has written, Prashant is also writing. So you take the unadjusted odds and then value of that, probably the p-value, and those variable who have got up till 0.2, you take that. There can be another criteria like from the review of literature. If you think that a particular variable is of interest to you, then you can take that also as a clinician. So, but it is a less likely chance that the variable showing a higher p-value in the univariable analysis is going to be significant. So in this, there's a beauty of this Jamovi that it gives both the unadjusted and adjusted in the single output. So in the same, this thing you can check. Now there's one more thing that there should be an assumption of the, before I go into this, I will show the assumption checking also. The second thing is regarding the sample size. So in any survival analysis, especially in this Cox proportional hazard, because you are making a model. So for model, what is the criteria? So number of variable, at least 20 out of 10 to 20 generally we say. Minimum of 10 to and maximum of 20 outcomes should be there per variable. That much sample size should be there. So in our case, it is, if you see the event, it was approximately 130 or something like that. So how much variable I can take? If I take 10 as this thing. So at least that much sample should I have. Otherwise, you cannot take many variable in the model, because then your model will not be it will not have a good predictive accuracy. So here I will show you, before I go to this, I will show you how to check for the assumption. So I said you regarding the proportional hazard. So proportional hazard you cannot check in Jamovi. For that you have to go to SPSS. So in SPSS, I'm just showing that there is an option of the log minus log curve. So if you go to analyze, go to survival and Cox regression. Again, I will enter this. This is the same. You can import it in the SPSS also. So this is the time to event. And this is your event. You can define event as 1. Continue. And then probably covariate if you want to enter like here. You can enter the covariate, gender, marital status, education. And then here you have to classify the categorical. So this marital status, gender, education, this is categorical. I am not changing the category. Okay. This continue and then go to plot. So plot here, there is a log minus log curve. And if I want to change it with this, then you can press on continue. Okay. And you can see the log minus log curve. What happened? Okay. So you can see this log minus log curve. So this is nearly, this distance is constant and it is not crossing here in the majority of the part. So if they are going parallel and if they are not crossing, then you can say that the proportional hazard assumption is met. Now coming to the another assumption, that was the multicollinearity. So for that you have to draw a correlation matrix. So that is there from the regression. So click on regression, correlation matrix. What are the continuous variable in your data set? So it is the breastfeeding, education, gestational age, birth weight. These are the 3 and now you can see the value of correlation coefficient. So you can see that this value of correlation coefficient is very less. It is 0. Breastfeeding, this education and gestational age. This is also very less. But this has got a very high correlation coefficient. Gestational age and birth weight. So in that case, you will take only one variable because then you will not come to know whether it is due to gestational age or it is due to the birth weight. So you can take one. So if I take like birth weight, I'm not taking gestation. Or if you think that you want to take gestation, then you can take gestation. So I will not take both these two variables and I will report that there was a multicollinearity between the birth weight and the gestational age. Are you getting it? How to check for the multicollinearity? Yes? No messages? No messages in the chat box? Should I repeat it? Complete silence? Priya. Okay, repeat it. So repeat from which point? Can you guide me, Priya? Like, can you unmute? Anyone can unmute and like you
Yes.
people can speak.
Yes, ma'am. Like here, the gestational age is coming significant, and birth weight with education is significant, but birth weight with gestational age is not significant.
So see, my aim is not to get a significant correlation. Why?
Okay.
That means, yes, you can say in one way you are right, that if it is significant, that means I should not use this. I should not use both these as a predictor variable. Are you getting my point? If the value of correlation coefficient is very high, then what does this mean? That you can replace one variable with the other? Am I right?
All right, ma'am.
Like in this case, if there are two, can you recall that I told that if there are more than one continuous variable, then you should not have the two, both the variable as a predictor variable, because then you will not come to know whether it is due to the birth weight or due to the gestational age, because both are very highly correlated. So in logistic regression also, this assumption you have to write. If there is more than one independent variable, which is a continuous in nature, right? So if it is a high correlation coefficient, you will take only one variable as a predictor variable. So it is up to you. You can take either the gestational age. So why then when you go to this window, this one multivariable, then I will not. So this is the window for continuous variable. So I might take gender, marital status, education here. I might take this breastfeeding education here, but both gestational age and birth weight I will not take. I will take either of these.
Madam, one doubt.
Yeah.
In previous in logistic regression, we mentioned that if the correlation value is greater than 0.8, greater than or equal to 0.8, we will consider it as multicollinearity. So is that the same assumption here also?
Yeah. It is the same. That's why I said that it is the same. Ideally, for multicollinearity, this is the VIF and tolerance. That is the better value. That is the better estimate. But
Yeah.
that VIF and tolerance you will not get here as a part of the what you say, this Cox proportional regression. You will not get it. So that's why you have to check with this correlation matrix.
But what if we check that there and then coming
Yes.
here?
Yeah, you can do that. You can do that. But I just want not to confuse you people because I have not taught you logistic regression. But again, those of you who know that in linear and logistic, if you can check on that platform, you can report the same thing here.
Madam, one more thing. Is there any variable that number of variables we need to take? Here you have taken 3 variables to check the multicollinearity. Is there any the number of variables there? How much we need to take? Is there any
No,
cutoff there?
actually, it depends on what predictor variable you want to take. So here there were 3 variables which were continuous in nature. You can see
Yeah,
all other are categorical in nature.
yeah.
So we'll take only those variable for this multicollinearity which are continuous in nature.
Okay,
That's
okay.
why I took 3.
Mm.
If there
Okay.
are, if like in if there is a modeling where there is only one continuous variable, like age,
Mm.
then you don't need to check for multicollinearity,
Multiple.
right?
Yeah.
Because you
Okay.
have got only one continuous variable, then why will you check for that?
Okay.
Uh,
Okay.
Prashant is writing how to decide which is to be removed. It is up to you. Like you can have one, this birth weight or gestational age. It is up to you. Or what you can do, you can check. I'll show you how to decide. You can remove one and see the HR, and you can remove the other and see the hazards ratio and see the difference. That way you can check. Right now, I have not I have included everyone. I have not like removed these. Although there is a multicollinearity, I will report that there's a multicollinearity between gestational age and birth weight, and then we'll see. So this is the and in this case, what you can do, you can convert it into the categorical also. If you want to have both as a part of your predictor variable, then you can classify birth weight. We have taken it as a continuous. So you may like classify it as a low birth weight and high birth weight, like more than less than 2.5 kg, more than equal to 2.5 kg. Similarly, gestational age you can define as preterm, term, and post-dated. So you can convert it also as a categorical if you still wish to have these variable in your model. So this is the output. Once you enter all these variable, you can see, like I said now, that this HR multivariable and univariable. Let me focus now. Focus on this table. This. So in a part of this table, it gives you both adjusted and unadjusted. This one. So right now we'll focus on this. So you can see, like if we have decided that we'll take only those variable where the p-value is still 0.2, like Prashant has, and many of you have told. So in this case, gender is 0.2, so we'll take. This is 0.02, so we'll take. This is 0.005, so we'll take. This also we'll take. So all are like significant. So we are including everyone in the model. So now, and if you focus, so if you see, this gender, this has not changed much. This is the unadjusted. If you see the adjusted also, it is 0.84. But you can see that it is not, this significance did not change. It is still 0.2. Then coming to the other, like it is 1.44 marital status. So how do you interpret this? If you see the significant, what all are significant? This is not significant marital. This is significant. Education is significant. Breastfeeding, this thing is significant. And this gestational age, these are all continuous. So this is also not significant. And birth weight is also not significant. You can see here. So these are, initially they were significant. If you see the unadjusted, these were significant. But when you adjusted it for the other variable, I think there are only two variables which are significant: education and the breastfeeding education. This breastfeeding education is the continuous variable, like number of sessions which the women got during the prenatal period. And again, you can have like skin to skin contact also I can add. Like maybe you can enter this here as a part of this. If you enter the skin to skin contact, then you can see right now again, there was a change. So this marital status is initially it was significant, but right now it is not significant. So we'll see this one by one. Let's see first this gender. I'm focusing. If you see the unadjusted is also 0.2 and the adjusted is also like 0.82 and 0.85. So if I want to do the interpretation, although it is not significant, what interpretation should I give? So it is 0.82. So how did we learn? That HR minus 1. So HR minus 1 will be your what? Here it will be how much percentage? 0.82 minus 1. What percentage will it have?
18%.
18. But the sign will be?
Minus.
Minus. So you will write that since the reference here, it is the male, because you can see the male is blank and this is given as a female. So the female was having, they had a 18% less hazard of experiencing this event, which was not significant, right? If you don't want to have it in percentage, you can express that females, it was protective because it is less than 1. So female gender was protective for this, and females were like 0.82 times experiencing event as compared to the male babies. If you remove this gender, because this was not significant, so if I remove this, then you can see, then again it will change, like marital status, it has become now significant. If you have this this gender, it was not significant. See, if the gender of the baby was there, this multivariable marital status, it was not significant. It was 0.06. But when I remove this gender, then you can see that it is now significant. So similarly, you can have an interpretation of this education. Education, this is not significant. The skin to skin also, this is not significant. So significant is this breastfeeding education. The number of sessions that the women took during the antenatal period. And these two are, again, they are not significant. So for this was for the categorical. For the continuous, how will you write? That for gestation age, although that is not significant, but this is again similar to the logistic regression or the concept. Here you can write that by increasing the 1 week of gestational age, there was this is since 0.78. So it is less. So there is a 22% less chance of experiencing that event, because this is minus. Are you getting it?
Yes, ma'am.
Yes.
One thing is that due to multicollinearity, you said that we can choose among either gestational age or birth weight.
Yeah. So
actually,
actually,
if you remove one of them, the other becomes significant.
Yeah. So yeah, thank you, Ria. That was my next step, but thank you. Yes, you are right. So initially I took both birth weight and the gestational age. Then none was significant. You can see here, both of them were having non-significant. If you remove one, then you will see that the other is significant. Can you see? Although it is 1, so it's better that you remove this birth weight and have this gestational age. Then it is 1 point. This is 0.83. Right. That means by increasing 1 week, the event experience is 17% less. Right. And this is significant also. So now can you see the problem of multicollinearity, Dr. Prashant, that if you have both the variable in, if it is like there is a correlation between those two variables, it was undermining the effect in the model. And then you see this last line, this is the model matrix. So this is writing that number in model is 200, missing is 0, and number of the event is 170. Now, can you see this word concordance? It is 0.634. What is this concordance? So basically, this concordance is like a C index. We also call it as a C index, and it is very much similar to that AUC, that area under the curve, which I know many of you know that in ROC we have learned that area under the curve is the discriminatory potential. So similarly, it is the diagnostic, the accuracy of predictive accuracy of this model is the C index is 0.63, which is okay. At least it should be 0.7, but you can report it 0.63. And then the R square is 13.2%. So that is the interpretation. So if you see the article, let me show you the article. Where I hope it will get open. Just a sec. So we have shared this article with you people. Yes, so we created this data set based on this article, breastfeeding education, early skin to skin contact, and other strong determinants of exclusive breastfeeding. So could you people read this article? I don't know how many of you have read this, but if you see here, the statistical analysis, I'll show you results. Okay, they are statistical analysis. So yes, can someone read this aloud? Who will read this? No volunteer? Priyanka?
Yes, madam.
Okay,
Shall I
sorry.
tell, madam?
Girish, yeah,
Dr.
please.
Girish.
Yeah,
Yes,
Dr.
madam. Statistical analysis and sample consideration using early skin-to-skin contact as the main explanatory variable. We performed the sample calculation by using the following parameters, considering the incidence rate of abandonment of exclusive breastfeeding was 2.8 events per 100 patients days. Among those newborns who did not receive early skin-to-skin contact in bracket unexposed, we observed that with an alpha of 0.05 two-tailed and a beta of 0.2, the minimum required number of patients in the group with skin-to-skin contact was 204 patients and 42 in the unexposed group. The final sample constituted 365 DIs with 302 exposed patients and 69 unexposed patients, assuring statistical power. See outline supplementary material for further details, madam.
So we are not going into the, because sample size, we are not focusing on that. But you can see that now. Can you read this, Dr. Girish?
Yes, madam. I'll read. Descriptive statistics were performed using percentages for categorical variables and median time, that is P25 to P75 for discrete variables. We performed a log rank test for equality of survivor functions to assess differences in the duration of exclusive breastfeeding. Then we estimated the crude and adjusted hazard ratio for each explanatory outcome. In that sense, we built multivariate Cox proportional hazard models to evaluate the independent association between each explanatory variable and actual time in days to abandonment of exclusive breastfeeding. We built a saturated model including all the individual covariates. Then based on previously established criteria, we eliminated covariates with p-value more than 0.25 from significant covariates that were retained in the model. Confidence intervals 95% of the hazard ratio and their corresponding p-values were calculated. Once the parsimonious model was obtained, we compared both models and choose the final model according to the level of its significance from the likelihood ratio test. Okay,
so
madam.
just yeah, thank you so much. I wanted to highlight few things here. So there are two terms which you are seeing here: saturated model and parsimonious model. So saturated model is when you take all the variables, and when based on basis on your this 0.2 cutoff, when you remove those variables which has got a p-value of more than 0.2, then that model is the model is known as the parsimonious model. And here, like in this case, you are not getting like model 1, 2, and 3. So that you have to. So Dr. Girish, we have shared the reference article with everyone. Probably in the mail also, but we'll share in the WhatsApp group again.
Okay, ma'am.
And so this is the final model, and then they have estimated this Cox proportional hazard model, and they have given like number of missing data. So the missing data was less than 1%. So they employed the complete case analysis and estimated statistical associations. Now, to test for potential effect modification, they've stratified the analysis according to infant sex, which I was telling you, like gender. Additionally, they performed several secondary analysis to assess the sensitivity of our estimate. Right. And they ran the final model excluding. So they have excluded those with no education and C-sections and those things. So now coming to the table, if you see the table, this is the baseline characteristics of like, this is the plain descriptive statistics, which I have shown you. You can do that with the descriptive tab of that Jamovi. They have just given the percentages, frequency, and this is like, again, the same continued one. Now coming to this table, this is the table which you can see here. Like these are the explanatory variables. So initially you consider this like this adjusted HR they have written, but this p-value which you are seeing, these two are together. This crude and this one, this two is together. So this was the unadjusted, right? This is like, let me show you, both in the same. Let me drag this. This is not getting dragged. So what I can do, I can copy this. I can paste this on a Word document because I wanted to show you people simultaneously. So I'm pasting this table. Although there are less number of variables. No. That is okay. We can see that. Still we can see. And let me show you that article. Yes. So you can see here that this is again this crude HR. So these are the crude HR and its p-value 0.93. And this is again univariable, which you can see here. The p-value, the confidence interval, and this is the univariable. And the multivariable, now what they have done, if you see this, the second section, this part is the saturated model. That means they have taken all these variables, up till this. They have not taken these. Why? Because they have decided that this crude HR, all the values, it is the non-significant, this they have not taken, like time ligation and all. And in this saturated model, where they have taken all the values less than more than 0.2, like you can see this one, this variable was more than 0.2. So they have not taken here in the parsimonious model. Similarly, they have taken all these three. This is again 0.8. So it is more than 0.2. So that's why they have not taken it. And this is also 0.85. So they have not taken here in the main model. So they have taken only the marital status, education, socioeconomic status, and session of the breastfeeding education and skin-to-skin contact. So these were the variables which they have taken. And if you come down and if you see, they have also explained like in the footnote. Can you see this footnote? Yes, so can someone read this? Dr. Girish, can you read this again?
Madam. There was found co-linearity in the models between early skin-to-skin contact and joint accommodation, timely ligation of umbilical cord and breastfeeding within the first hour of life. Those variables were excluded from modeling the saturated model.
So this is like same, which we have shown you here in the JAM movie, that since there was a multicollinearity, so we have removed those variables showing the multicollinearity. And as Dr. Binu said, that you can decide the multicollinearity from the logistic regression, this linear and logistic regression output also. There you will get that multicollinearity. You can see our earlier video on the linear and logistic regression. So this was regarding the graph. Now I have not told you many other options here. So here there's a plot. So if you click this, you can see that it gives a plot like this. So this is, can you see it gives you all the variable, something like a, with the confidence interval, hazard regression plot. So you can copy paste this in your result section and you can like give, this is also one way of expression. Now there is the option of adjusted survival curve. So if you want to adjust, like if I want to show this against marital status, comparing like or keeping all other variables adjusted, then this adjusted survival curve will also appear. See, I did not click that, that's why it was not appearing. So you can see this is the adjusted survival curve for the marital status. And then here you should change the plot time. So my total follow-up time was 180 and the duration was 30. Risk table, if you wish, you can have. This was a similar which we did with the earlier options. So that okay, that is not there. Here you can see that is there with the Kaplan. So this adjusted, it is not showing. So this is the one option which you can just the above table, it is representing as a this regression plot. Now we have shown you one way of doing this. Now there's other way. This was regarding the multivariable, but this Kaplan-Meier can also be done by using this univariate survival analysis, like which we have seen yesterday. So you can perform that also. There's a difference, like if you perform a Kaplan-Meier survival analysis, use this option, then you will not have an overall survival rate. Like if I will show you, if you want to have this outcome as a gender, and this time to event you take here, and this event you describe here, termination, and if you want a Kaplan-Meier survival, this is the plot. So survival plot, if you plot, then you will see that you will not have an overall plot here. You will always have this plot under this male and female. Let me change the axis. So it was 180 and this was 30. But if you use this option, that survival, this one, so here you can have an overall survival, even if you don't define the group. Like if I include here the time to event 1, and this is the event, and this is your termination of breastfeed, then you can have an overall survival also, this graph. And this median, that option is not there if you use that univariate. So are you getting what I'm trying to say? This overall survival, you get only when you use this death watch option. When you use this univariate survival, then you will not get a graph of this overall survival. So have you understood? Then we may go to the breakout room and we may practice there once again. So it is requested from all the mentors, kindly emphasize and ask from the participants regarding the interpretation of hazard ratio, both for the categorical variable as well as for the continuous variable.